give a brief introduction about sir before we start the session. So, sir, I'll be just sharing my screen briefly, and then I think. Okay. Okay. So it's our pleasure to have Professor Rangan Banerjee with us, and Professor Rangan Banerjee is the Forbes Marshall Chair Professor and Head of Department of Energy Science and Engineering at IIT Bombay, a department that he helped start in 2007. His areas of interest include energy management, modeling of energy systems, energy planning and policy, hydrogen energy, and fuel cells. He is on the editorial board of Energy for Sustainable Development, International Journal of Sustainable Energy, International Journal of Sustainable Engineering, and International Journal of Thermodynamics and Frontiers in Energy Research. He has been involved in setting up a megawatt scale solar thermal power testing, simulation research facility sponsored by the Ministry of New and Renewable Energy. He's a member of the TIFAC Technology Vision 2035 EPICS Committee and chairman of the Energy Technology Team. He was a convening lead analyst for the industrial end use efficiency and a member of the executive committee for the Global Energy Assessment 2008 to 2011, coordinated by the International Institute for Applied Systems Analysis. He was a member of the working group on new and renewable energy for the 11th and 12th 5-year plans and a member of the Planning Commission's Integrated Energy Policy. He was a member of International Committee to review UK's energy research program in 2010. He has co-authored a book on planning for demand-side management in the power sector, a book on energy cost in the chemical industry, and a book on engineering education in India. He has conducted 2 international training programs on solar energy and several national programs on renewable energy and energy management. He is also an adjunct faculty in the Department of Engineering and Public Policy at the Carnegie Mellon University. He has been the Dean Research and Development of IIT Bombay. He has received the Excellence in Teaching Award from IIT Bombay and is a fellow of the Indian National Academy of Engineering. So it's a great honor and privilege to have Professor Banerjee with us, and he'll be giving the introductory session and sharing some insights, some valuable insights and concepts of modeling of energy systems. Thank you so much, sir, for being here.
Good morning, and it's a privilege to be here in a course organized by Professor Ridham Singh, and also I think it's a sort of second best in terms of earlier. I would have preferred to have been live there at IIT Roorkee. I think that visit is pending, but given the circumstances, we have to settle for the second best. So I guess we have about an hour with us, and we'd like to have this in to try and do this in as interactive a way as we can, given the circumstances. So you please feel free to put your questions and comments on the chat, or to raise your hand, and if you are you can even ask your questions live. So what I'm going to talk to you about in this short time is about energy, about modeling of systems, and specifically with respect to energy systems. So we will, I hope the slides are visible. Can you see the slide? Can just post it in the chat saying that, is it visible to you? You know, unfortunately, in the normal case, what happens is you look out and you see whether people are listening. You can you can understand what's happening. Okay, you can see the slides. Okay, so we are going to talk about modeling of energy systems. And the way we've planned it is I'll start with a few basic things about modeling of systems and energy systems. And I am sure all of you are faculty members, so you already have this background, but this is sort of in the form of a revision, and this would be about a little less than half of that initial lecture, which is setting the context in terms of understanding why we model, what is an energy system, and then I will give you different examples from research that has been done by our students, yeah, in the form of different kinds of models. Given the time, I won't be going into details of each of these, but this will give you a glimpse of different kinds of examples of modeling. So with that, I hope I will be able to set the context, and then we will, if you have any questions or queries, we can go into some more details. That's the way I have planned it. So the first thing that we need to ask is, what is an energy system, and why do we model energy systems? So as people, as faculty members who are interested in energy, you would realize that finally when we look in terms of, we would like to see what is an energy system. Every activity that we have, every human activity requires some form of energy. And we need energy for each and every aspect of our lives. So when we look at an energy system, we have energy. There is this energy flow diagram, and this is something that I'm sure most of you are familiar with. There is energy that is available in nature. This is called primary energy. This could be the conventional fossil fuels in terms of stocks, coal, oil, natural gas, or it could be renewables, solar, wind, biomass. And this primary energy that is available in nature is extracted and made useful to us. In doing that extraction, when you take coal, you mine the coal, you wash it, you beneficiate it, you put it to an energy conversion facility, maybe you generate electricity with it, you have a power plant, you get this secondary energy source which is more useful to us. That secondary energy source, for instance electricity, goes through a transmission and distribution system. Then you have the electricity that you buy. For instance, IIT Roorkee might be buying its electricity from a DISCOM, the distribution company which is in the state, and that is coming to your own substation. That's the final energy. That's what is the consumer is buying. That's the final or the delivered energy. That final energy is also going through a set of transformations and being used in the equipment. And so for now, for instance, you are using a laptop or a desktop, and that has getting the electricity from your supply system. There is a conversion efficiency in that, and then you get the useful energy. So finally, what we need is the useful energy for our end use activities, which is basically illumination, computing, food, distance traveled. In order to do that, we need some useful energy. For that useful energy, we need to take energy from the energy that is available in nature. Each step of this conversion has associated with it some kind of losses. So if you need X units here, you probably will need 2X or 3X of primary energy depending on the kind of efficiency. So whenever we look at an energy system, it could be something which we are using at the consumer side, it could be a transmission distribution system, it could be a power generation system, it could be a system where you're looking at all aspects of it. So this is in terms of an energy system. And in all of this, we have different types of decisions that we are looking at. We could think in terms of decisions where we are deciding whether or not we should put in a pumping system where you have a pump where you're pumping water. Should I put a variable speed drive on the pump? It's a yes no kind of decision. Or I am looking at a boiler or a furnace where I'm getting exhaust gases going out. Should I put a waste heat recovery device? Or I am looking at, this is a yes no type of decision. We could have a best possible amongst option. I have an island in the Lakshadweep where I want to electrify it. Should I take the electricity from the mainland through an underwater cable, or should I put a diesel engine generator? Should I put a PV plant? Should I put a biomass? So there are a number of different options. We want to choose what is the option. We can look at a system or a component design. You're designing a heat exchanger, or you're designing a maximum power point tracker, or an inverter, or a motor, or so this is a component design, or you're designing a system, the entire power plant. You have a plant which is operating, we decide on operating strategies, or at the government level, we decide policies. So these are all the different kinds of decisions. Many of these decisions, given the fact that an energy system is linked and complicated, many of these decisions are non-trivial, and then we need to have analysis, and we need to have these decisions based on sound principles and based on analysis, and that is where again modeling can come in. We can look at different kinds of perspectives from the point of view of the end user, the manufacturer, the utility, the society, government, or others. So the question is, what is a model? And what models are you familiar with? Why do we need a model? These are the three questions which we would like to ask. I'm sure all of you have dealt with models. So can you just put in the chat some answers to these questions from your perspective? What is a model? What models are you familiar with? And why do we need a model? Please go ahead. Or if you want to raise your hand and unmute yourself and speak, that's also okay. Quickly, I'm sure each of you have done variety of models. I can see someone's raised hand. Munesh Kumar Singh, please unmute yourself. Go ahead. Please speak. Munesh. Can't hear you. Please unmute yourself and speak, Munesh. Otherwise, just put it in the chat. Not able to hear. Okay, Kiruba Devi. Unmute is, oh, okay. Unmute is unavailable to attendees. Okay, I didn't realize that. Okay, that constrains us, but just put in your chat whatever you want to say. I'm sure each of you have actually used models. Please go ahead and write in the chat the answer to the questions that I have put down. What is a model? What models are you familiar with? And why do we need a model? Anything? Okay, I guess you're hesitant to put things in the chat. Let's just see. You can look at a definition. The dictionary definition of a model is a replica of something or a representation of something to be constructed. In the typical English dictionary, we are looking at a model which is a replica of something or a representation of something to be constructed. That's a noun. Model of a building. And verb is a model, produce a representation or simulation of, or to construct or fashion in imitation of. So model is a representation of reality. And why do we need a model? So essentially what happens is that in all aspects, when we look at any of this, we are trying to construct a building or we are building a power plant. When the actual process of doing trial and error, making different kinds of equipment or systems without analyzing it would be a very costly process. So we need to understand a priori before we actually make it. We need to understand how it would behave. And in order to do that, we make an assumption, we make some assumptions, we replicate, we create a synthetic system which is very similar to the system that we want to build. And that is, we are representing those elements of reality that are relevant to us. And yes, now I see that there are some answers: model to support analysis, specification, design, verification, validation, as well as communicate certain information. Yes. Model conceptual or mathematical 3D replica. Yes, it could be a physical quantity which represents. So essentially what we do is we represent reality, and we represent those elements of the reality that we are interested in, because we cannot replicate every element of the reality. So we will make relevant assumptions and create something for the purpose of the decision that we are trying to support. Okay, so it's a representation of the reality, and it would represent those elements of the reality that we are interested in. So we will start off, when you look at the model development, we start off by defining what is the goal, why are we doing the model, what decision are we trying to support. We analyze the situation, identify the variables. In case there is a design thing, we can also decide the criteria. We establish some of the equations and relationships between the variables. We analyze the problem, synthesize the problem, link up all these coefficients, and then we create basically the first cut model. We test that model for internal consistency, validate that model with actual data, and then we have a model that we can use to make inferences and prescribe actions. So that's basically, this is the set of steps in model development. And how do we decide whether or not a model is good enough? So for the same context, depending on the type of decision context, we can have different assumptions and we'll get different types of models. So again, depending on, suppose you are designing something, many things are open to you, many choices are open, you'll have one particular type of analysis. But if you fix, once you choose and you have an equipment, you have a power plant, you want to see how it will perform, then it gets constrained. And then then you have a different type of model. So if you want to find out what is an operating strategy, that would be a different kind of model. So whenever we judge a model, we must look at it in terms of its ability to give the inputs for the decision it is intended for. We also want to see what is the computational effort and the cost and the computational time. We would like to judge the model in terms of its accuracy of prediction and its reliability. So these are typically the kind of parameters which we use when we try to do the model. Okay, now I try to give you an example of a model from something that many of you would be familiar with. I guess I'm sure most of you are many of you cricket enthusiasts. Are you watching and following the IPL, for instance? In the IPL now we seem to have many of these things where the IPLs are tied. It's the probability of having so many ties in a few games is actually it's quite surprising that you have so many tied games. But if you look at if you look at cricket before the IPL, you had the most common and fun form of the game was the ODIs. And in the case of the one-day internationals, earlier it used to be 60 overs, then it became 50 overs matches. You had this problem when, what happens if one team is playing and has played its 50 overs and then it starts raining, or in between it starts raining. So essentially this was the problem. You must have heard of the Duckworth-Lewis method. What is the Duckworth-Lewis method? What does it do? Please put in the chat. See, I'm trying to interact with you. Unfortunately, it's not as easy as if you were in the room and you asked you questions. So, do you know about the Duckworth-Lewis method? What is the Duckworth-Lewis method? So essentially, this is a model, and Duckworth and Lewis are both statisticians, and you can look at this there is this paper which you can see, a fair method for resetting the target in interrupted one-day cricket matches, and Duckworth and Lewis. And what they did is they analyzed the ODI scores, and they said that we look at the total number of runs that you can make is a function of two variables, two resources that you have. One is the number of wickets, and the second is the number of overs. So these are the two resources, and then they basically did a regression with the past data, and then got a correlation which would adjust the number of overs based on the number of wickets. So you had basically as per the wicket, and yes, we've got an answer as per the wicket and over consumed, the run is estimated. So you have this estimation, you have two resources which are overs and wickets, and then you have an asymptotic average which is conducted based on wickets and the number of overs. And these are these correlations. Duckworth and Lewis put this. They put it in the form of a set of equations. They published a paper. They also patented it. And of course, Duckworth and Lewis became millionaires as a result of it. They created a company which sort of takes this. And essentially what happens is this is an empirical relationship between the different data sets which are there, and that is used to curtail, if rain curtails the prey, depending on the number of overs with the number of runs, your targets gets reset based on this. There have been critics of this and saying that now the data sets are different as well as the resources are different, and this Duckworth-Lewis method should be modified. There are some papers which are talking about this, but this is to show you one way in which you can use a model. You can use the past data, create a correlation, use that correlation to see what is this, and this has been used in the game of cricket, a game that is familiar with to most of you. So when we think in terms of a model, we have two types of models that we will discuss. One is a simulation model, and the second one is an optimization model. So when we talk about simulation, we are looking at typically a system simulation where a system, I'm sure many of you teach thermodynamics, so you look at a system as that area which you are interested in. In the case of modeling, we are looking at a system as a collection of different components whose performance parameters are interrelated. And as a result of this, basically what we need to do is we need to club these components together and see what happens when you put them all together. We means observing a synthetic system that imitates the performance of a real system. So for instance, I have in a location, in a remote location, I have a pumping system, and which is currently running on an electric motor. The power supply is erratic. I have someone is willing to donate me a diesel engine. I want to know if I connect the diesel engine with this with the motor with the pump shaft, how much output would I get? So I know the diesel engine characteristics. I know the pump characteristics. I correlate these in the form of equations, put them together and create a synthetic system with these two, and then see how it would perform. And this is basically a simple example of a system simulation. And why would we like to do a system simulation? Often what happens is that when you put different components together and you are, for instance, you are looking at something which is an off design point or an operation at a part load. So you would like to see how this would work, how your whole system would work without actually first building that system. And so this is what system simulation is there. For system simulation, what would we need? We would need the characteristics of the different components. Let's say we have a power plant. We would like to see what is there in the boiler, which is the fuel we use, what are the characteristics of the boiler. And then we have that going through some heat exchangers, then it goes through a superheater, and you go through a turbine, then you have the condenser, you have a boiler feed pump. Each of these components has its own characteristics. When you link them together, you get a systems, you get a model which actually tells you how the system would work. You need the properties of working substances. So in this boiler steam example, we need the properties of water and air, when we need the conditions imposed by the surroundings and environment. With all of this, we then get a set of equations which characterizes the equipment that we have. And in this case, this is completely specified. That means there are no degrees of freedom. We can actually see that under different conditions how it would perform. And that is where that is called a simulation. That means you put some input variables, number of inputs and number of outputs are the same. You form a sets of equations which you then solve, and you can solve it. On the other hand, you have situations where you have the possibility of design and you have the possibility of choice, and you have variables that you can choose. That means you have some degrees of freedom. When you do that, you typically, what we do is we optimize. We try to get the best performance. And this is, if you see the book, there's a book on optimization. It's a classic book, Bettler and Wild. That should be Wild. And in this, he said the man's longing for perfection led to the theory of optimization. The German philosopher in Leibniz in 1700s has said the aim of princes and philosophers is to improve. So in everything what we try to do, we try to maximize the good or minimize the bad. And that is what is the theory of optimization. We try and create a function which correlates whatever is the parameter which we are trying to maximize or minimize, and based on that we make our choices. So this is what is called optimization. So we can put down all the equations and the constraints. Some of the constraints are from the variables, some of the constraints are from the external environment, and based on that then we put some objective function which may be minimizing the cost, maximizing the reliability, maximizing the output. So this is different from the simulation, because in the simulation everything is specified. We just run it and we get what will be the operation, what are the sets of variables. And here we are exercising our choice. There is a value judgment in the in deciding what is your objective function, and we are either trying to maximize or we are trying to minimize. And so these are the two categories of problems, the simulation and optimization, and these are the two different categories of models that you would encounter. Typically, in a general condition of optimization, it would need to have an underdetermined system where there is a degree of freedom greater than 1. We would have an objective, and there would be constraints or restrictions, and typically there would be competing influences. So if you look at a pipe carrying hot water and you're looking at putting insulation on that, what happens is that if you look at the insulation and if you increase the thickness of the insulation, the capital cost that you have initially to put the insulation, some fixed cost and a variable cost, as you include the layer of thickness, the capital cost starts increasing monotonically with the thickness. And the operating cost, what happens is that the heat loss starts decreasing. Because the heat loss starts decreasing, your fuel cost gets decreased, your operating cost gets decreased. You can take the capital cost, annualize it, and get a total cost. And because you have these two competing trends, one is operating cost starts decreasing with thickness, and then of course it sort of converges, and the capital cost starts increasing. Because of this, you have the competing influences and you get an optimal thickness at which you can operate. So this is just to give you a very, very simple example to illustrate the trade-offs that are involved and the reason why you would have an optimal. And of course, now what happens is, depending on the characteristics, you can have a fairly complicated set of equations and constraints, and you can go ahead and derive and then get what is the thing. So in all of this, you would have some elements of reality, some elements of assumptions, and with this we identify, create the model, and then do that. And we talked about in an optimization scenario, we talked about different types of criteria. Usually, most of our decisions are based on costs, either the initial cost, operating cost, or the life cycle cost. We can also look at reliability, availability, or unmet energy in an energy context. Increasingly, most energy systems are now focusing also on emissions, and we can look at local or global emissions. We can look at sustainability. We can look at equity. There are many different types of criteria, and sometimes we also run it with multiple criteria. Now, it's not necessary that we always optimize, and this is something that you may or may not have come across, but this is something that I would urge you to read these papers. Professor Herbert Simon, he was a Nobel laureate, he was a professor of Carnegie Mellon University, and he talked about rational decision making in business organizations. And he came up with this concept that when you have a large number of options, it is very difficult for any individual or company to really explicitly consider all these options. So you have this bounded rationality, and you need to look at a subset of these options. And often what happens is that we don't necessarily have to go for the best. We can satisfy. That means any solution that meets our constraints and is within a particular cost and is good enough, and we don't need to necessarily always think in terms of the best. You look at your decision in terms of how you spend your time, whether you spend your time on your work, on your preparation for your lectures, on your research, on different kinds of things, and the time which you give for leisure. If you want to create a sort of objective function for yourself, which is maybe maximizing some kind of a utility, and you can try and find out what would be an optimal set of things with a different set of constraints. But in many cases, as long as you meet each of your deadlines and you have a certain amount of leisure time, you are fine with whatever solution you get. It's too much trouble to try and find an optimum. So in many cases, really we don't necessarily optimize, we often satisfy. And this is something qualitatively that you may want to read up. This is interesting to do. Okay, so now this is, I will just pause here. This was basically the overall context of what is a model, why do we need to do a model, and how do we judge a model, what is the difference between simulation and optimization. If you have any quick questions or comments, please put it on the chat. Otherwise, I will now go forward with my examples.
Also, I'm giving the permission to attendees to unmute if they have any questions they can ask right now.
Okay, great. Thanks,
yes.
Rhythm.
Yes.
So does anyone have any questions or comments? Please unmute yourself and speak.
Professor Banerjee, good morning. This is Dr. Adhikari.
Good morning, Dr. Adhikari. Please go ahead.
Sir, you have very clearly explained everything. You have mentioned about the reference papers also. Sir, is it there any preliminary level textbook for undergraduate students who will be doing projects so that this modeling and simulation kind of thing?
Oh yes, there are many. You know, the thing is that in optimization, I have a set of references at the end, and there are a whole set of different books on optimization, and there are also books on energy modeling, and there are a large number of papers. So I will give you those references at the end, and subsequently also, if you have anything, you can always send me a mail, and I will try to add. There's a lot of public domain material, no problem.
Okay. Thank you so much, sir. Have a nice day. It was a very nice presentation till now. I hope it is, again, it will be a very great presentation.
Okay, thank you. Any other comments or questions? Otherwise, we'll move on. Okay, let's go on. We'll take the questions then later. So let's look at, I'm going to give many different examples done mostly by our PhD and our master's students. And in each of these models, I will first describe a little bit the context what we are modeling for, what is the nature of the model that we developed, how was it validated, and what is the usefulness. So I have this 4-box kind of characterization, and this is just to give a sort of sense of how that model is used. So we'll have a number of these, and I'm going to quickly go through these, and depending on the time that we have, we can maybe deal with some of these in the Q&A session. So there are, I've classified these into a variety of things. That means we can look at equipment design, and I've got an example of that. We can look at system design. So equipment design, I'll talk about linear Fresnel reflectors. System design, I'll look at a glass furnace. I'll talk about microgrids and some buildings. Potential estimation, solar PV, system integration, again PV, and policy modeling, one example from energy. So there are about 7 examples, and I've added a few more in each of this. So in this case, we have 2 examples here and 2 more there. So about 8 or 9 examples. We'll quickly sort of give you, just to give you a glimpse. So this is an equipment design example, and here the idea is that you have these Fresnel reflectors, where if you look at a parabolic trough collector, if you Fresnelize it, you cut it into sections and you make them as linear Fresnel reflectors which are going towards a receiver. Now we want to find out this trapezoidal receiver, what would be the heat loss from its surface. So you have this receiver which is getting, you have these mirrors, the reflectors which are reflecting here. You have the working fluid, which is water, which is getting pressurized and heated and going into two-phase flow. And we are trying to see, based on the design of this, what would be the performance and what would be the heat loss from this system. So this is there's an experimental setup which we did along with an industry partner, that is KG Design at Coimbatore, and we put some thermocouples at different points. We basically, this model was to design this receiver, and we are looking at a 2-dimensional heat, mass, momentum, and energy balances. We use the CFD code Fluent, and then we built, we got correlations for Nusselt's number in terms of the Reynolds number and the different characteristics. So we basically got an improved usefulness, is an improved understanding of heat losses from LFR cavities, and then the effect of variation of different design parameters. This could be useful for component design. So this is the kind of correlation you can see, and these are the fluent sort of lines which show you the kind of temperature profiles and the heat loss from the surface. And this is the total heat loss as a function of the tube temperature. And so this is one example of a component-based simulation. Just to give you also an example, to give you an indication of how these Fresnel reflectors are used, this is a plant that we built. We were involved in this as IIT Bombay as a part of a consortium. These are parabolic troughs, and these are these Fresnel reflectors supplied by KG Design, where we take the water, heat it to, we get steam, two-phase flow. This steam gets superheated with the heat transfer oil, and we have a 1 megawatt output. So in this case, this was a test facility that we built. We also, in the plant, this was the kind of correlation. This is the oil field, this is the steam field, and this is the turbine. In this, we built a simulator because this was a 1 megawatt plant, but we wanted to be able to simulate the performance of this plant and then use it for different kinds of plants with different kinds of capacities.
एक ओवरऑल एनेबलिंग ऑप्शन है, पार्टिसिपेंट्स जहाँ लिखा है उसके बगल में. I'm sorry actually.
Yeah. So we had this simulator where you can use this performance data, and then you can actually configure different kinds of plug and play collectors, Fresnel reflectors, the turbines, and then see how it will perform. So you can design a 50 megawatt plant and then do this. So here this idea objective was to scale up. We validate it using the characteristics which are there in that, and then move on. So we looked at equipment design and then system design for solar thermal. Let's look at a second example. This is for energy efficiency. We are looking at in the process of glass making. Essentially, if you look at it, it is a very energy intensive process. So we wanted to create a model for the glass furnace and see what is the best performance that an existing glass furnace could have. And we were also looking at what possibilities for waste heat recovery. So in this, what we did is we broke up the furnace into different zones. We did mass and energy balances. We got heat loss correlations. We then took this model and validated it from industry. So we did field measurements for 9 industrial glass furnaces. Then we created an industry workshop. The idea is that any industry can use this model to put in different their furnace characteristics and find out what is the ideal target specific energy consumption per ton of glass for that, and then compare it with this. And this graph actually shows this comparison in the workshop for the industries that were attended the workshop and tried to put this. So if you look at this, what happens in this is an information flow diagram which looks at all the variables. You have the air flows and gas leakage, you have the fuel and the stoichiometric calculations, you have the calculation of the glass reaction, the furnace geometry, combustion zone, regenerator, heat of reaction, and then you have a total energy balance and fuel calculation. And this is the kind of measurements. These are the points at which we took temperature and flow measurements, combustion and the excess air. And with all of these measurements, we then could use it and then validate and use the model. So this, of course, as you realize, it's easy to put it on a diagram, but actually to take the measurements and then compute that and compare it with this is quite involved. And then with this model, basically we can create, see what is the actual specific energy consumption and what could be the target. And then finally what we did is we created a Sankey diagram, which you can see. You have some of the useful energy carried in the glass, some of it is being recycled through the regenerator, and then you have the different loss components. The interesting thing is with this, we could get also what is a target for that particular furnace. So you have a Sankey diagram and you have an ideal Sankey diagram, and this can help you actually, the model can help you. It's called model-based benchmarking to set a target that is more realistic for your company. So this was the second example. Let's look at another example, microgrids, isolated, or you can have grid support, and you can have various configurations. So we're looking at PV battery and storage with ultra capacitors, hydrogen storage. We want to look at an optimal sizing of the storage. We created a lumped parameter model for each component, and then we use the pinch analysis to do the balancing between the supply and demand, use the design space approach, and found out for different time horizons what kind of different storages would be suitable for this. Validation was done for a couple of sites where we have the load characteristics and the equipment characteristics, and this can tell you based on cost and reliability, you can get what is the target. So essentially what happens is this is the usage pattern, this is the solar insolation pattern, these are the different types of loads which have been put in the model, and you can see the different components in the system. We have the equations so that we see the battery pickup and the amount supplied, and also generation should not exceed the maximum power. We have a depth of discharge relationship, and essentially for each of the storages we find a region in which it can operate, and then based on this we can minimize the cost for a particular kind of reliability. And we tried this with different kinds of storage, and then we got optimum configuration with PV, fuel cell, hydrogen, etc. And the costs, and of course you see that these costs are quite high if you do an isolated system, 24-30 rupees, but that is currently the situation. Of course, as technology improves, these costs can come down. But this is a way in which we find how you look at meeting that requirement, matching the supply and demand in order to minimize the cost and identify different kinds of storage ratings. Let's look at buildings. Buildings is another very important area where you can have different kinds of models. Let's show you two types of models. One is which was done by one of our teams, Team Shunya, which did the for which was the first Indian team in the solar decathlon, where we built a completely fully functional solar house. And here the next part is when you look at a building and you try to simulate it. So this is where we use simulation with Energy Plus and Design Builder. When you try to optimize, there are a large number of variables. So what we did is we did a detailed simulation with the different variables. Then we used the Taguchi method to identify different sets of parameters, and we created surrogate models to approximate the simulation. And we used experimental design, the factorial design, response surface methodology, and then identified using an optimization with genetic algorithms the best space and the minimum cost solutions. Validation was used by using this method with Energy Plus, and we had an error of less than 10%. We did this for a typical two cases, Team Shunya, as well as a three-storied house in Delhi, which was a part of a particular competition where we had all the database data for it. And the methodology will reduce the computational time, and we can basically do a near optimal solution using our surrogate. This was a PhD thesis of Jay Dhariwal. Before that, let me just show you, this is the actual image of the Team Shunya house, 680 square foot house with 5 kilowatt PV peak on top, solar thermal. We used phase change material, and this is the compact kind of 2 bedrooms, one drawing and living room, which is also serves as a sort of kitchen and dining, and we have 2 bathrooms in this. And this was the kind of building envelope. And typically what we did is we started with the initial loads and then started putting different kinds of solar passive concepts, and we could reduce the total air conditioning requirement. This is a fully air conditioned house, to about 30% of that, and then met that requirement with renewables. And during the competition duration, you can see that this is a completely energy positive house. And this was first simulated using Energy Plus, and then we rebuilt it and then took that in the competition. And these parameters were actually monitored during the operation of the competition. Now we come back to the second thing where we were looking at creating a set of surrogate models. We created by doing the simulation, we created a set of surrogate models, and we optimized based on the surrogate models and got the optimization. So here we have, as you see, a whole set of discrete variables: window to wall ratio, the sensible heat gain coefficient, transmission coefficient of the windows, overhang depth, fin depth, a whole set of different parameters from this 3-storied building which is being designed. And in each of these there are different combinations, so you have a large number of combinations that you can handle. We simulated this using in Energy Plus, and after doing this simulation we got the performance and the costs, the capital costs and the operating costs, and then use this to generate empirical correlations. And these are some of the building correlations that were developed with these parameters. And with this, then we got a solution procedure where we use genetic algorithms to get the final solution. And then this is where we basically combined, because the large number of options that we have requires makes it untenable for complete optimization. And so we make an approximation, validate it with a detailed simulation and some performance data, and then use that simplified model to get the optimal. After we get the optimal, we can do a detailed simulation for the optimal case. So that was another context. The next case which I am going to show you is some work which was done by Professor Ridham Singh himself when he did his PhD, where we are looking at estimating the rooftop PV potential in a city. And the idea is that in the solar mission, we are supposed to have rooftop, but actually it's mostly ground mounted, which is going, rooftop is not growing at that rate. So the model has different components: estimation of the area, the insolation, the PV device and system characteristics. And then we validate it with samples for land use, comparison with literature, and we have load profiles, and this can be used for variety of cities. So essentially we have an area estimation block. We have a insolation block, which is the solar characteristics of a location, and then we have the PV system and device block. We combine this, and then you get the technical potential, and then you get at different kinds of over the period of the year what how much you can generate. So essentially we get, for a particular ward of Mumbai, you can see this is the map, and you can correspondingly get the GIS and satellite imagery, and you get the land use, land cover types, and then you get what is the roof area and the building footprint. And based on this, with the characteristic, the final model shows you this is the Mumbai load profile. This is if you had the total PV potential, this is the amount that you can generate, and then you can get the capacity factors for different ones. A comparative thing, the same thing which we now look at, if you had a large amount of PV in a system, we had basically thermal and hydro. And here this is the next model where we look at a hydrothermal scheduling, and here we use dynamic programming to see if you have increased PV and renewable share, how do you look at dispatch and how do you schedule PV. And so you have an algorithm for a case study of Mumbai, and this is again something which Dr. Rhythm had done. You can see details in some of these papers. We have each of these load profiles. You have some daily load profiles, and you have the scheduling of the hydro and the thermal given the PVs. Mostly these PVs are must run. We are trying to minimize the overall cost, and then you get for the city of Mumbai what kind of ramp rates. And these are showing you these kind of amounts which are being generated by different supply. Again, a simplified lumped parameter model which we had done. This was a dual degree project of another student. Aishwarya had done this, and where we are looking at an aggregate model with a base year, a load profile, wind and solar variability, a target year, demand growth rates, and then you look at future demand. So essentially what happens is we project the future demand, and this is the load profile in 2040, taking the Niti Aayog estimates. And then from that we have the PV and wind, and so we get what is the PV and wind generation in different hours, and we subtract that when we get the net residual curve that is to be met. And this is the final ramp rates which are required. We can cross check that and see whether or not the capability of the power plants are there. And this is what is called the duck curve. And again, depending on the different PV penetrations, there will be a point when we go where every amount of electricity which you are getting has to go through storage, and then that would, so essentially what happens is if you have a higher penetration of PV beyond a point, you start having to take everything to storage, so the cost will then go up. So that is something we are going to come to, that kind of system soon, as the PV penetration increases. Today we are not yet looking at that, but this is where again modeling can tell us a number of things. PV battery system, we want to see overall how sustainable is a PV battery system, and here we want to look at different types of batteries. We are doing a net energy analysis here to try and see cradle to grave or cradle to grave, and look at payback times. And this has been done, again, this has been done by Jani, and Dr. Jani, who has finished her PhD, and she's now teaching in one of the engineering colleges. We look at the amounts which we look for material, the manufacturing, the transportation, and then the end of life. And for each of these we can compute, and then based on the generation we can see how much is the embodied energy, how much is the energy payback period. These are the different components. The first part in silicon is per kg of silicon, then here it will be per kilowatt peak of panel. We get the total energy consumed, and then we can try this. We've tried different kinds of batteries, the lead acid, the lithium ion, and the nickel, cadmium, and sodium, sulfur, etc. A whole set of things. For each of these, we've compared them based on the energy component and the emission factor, energy payback uh, percentage of the cycle life, the net energy ratio, emission factor. So we are saying that when you have a new technology, we can actually look at the life cycle energy and life cycle emissions and use that as a basis for making your calculations. Okay, I'm sort of running out of time. I'm going to look at the last thing where we talk of not just we've looked at technical systems now, we can also club this with the economic system, and this is an energy economics model where we look at what happens when we have different sectoral mixes. Context is modeling framework to link energy, economy, environment, and this is not been adequate. We want to look at the impact of structure of economy and the climate constraint. What happens if you have more industry or more services, and then you go to this. There's a triplot which shows share of industry, share of agriculture, and if we go, we have two possibilities, a high services growth or a high industrial growth. If you have a high industrial growth, you would need much more in terms of energy. So we created a soft linking of different types of models. There's an input-output model for the economy. There's an optimization model, Merkel, for the power sector, and we tried to see what happens if we are making more investments in the renewable sector, different high services, high industry, and carbon constraints and restrictions on emissions or no restrictions on emissions. And we saw that there is some impact in terms of GDP and equity when you do this. So these are again some interesting things which come up in terms of modeling. So with this, what we've seen is we've seen a whole spectrum of different kinds of applications of models, from components to systems to energy economy systems. And just to repeat, models are representations of reality. They can help us in improving our decision making and or what if situations. There are value judgments. There are trade-offs between criteria. We can look at optimizing and satisfying. We should also look at the sensitivity of the parameters to the input parameters and look at how robust are our results. We can use blend of models and prototypes to develop future sustainable energy systems. Energy systems are in transition, and there are lots of challenges and opportunities for all of us. We need new modeling systems and new modeling paradigms to analyze some of these transitions. These are some of the PhD and research students whose results I have put, and like to acknowledge them. Also like to acknowledge Team Shunya and our National Solar Thermal Power Plant team. So with this, I will stop, and I will be happy to try and address any questions in the time that we have remaining. I guess we have about, Rhythm, I think we have about 10-15 minutes for questions.
Yes, sir. Yes, sir. We definitely have 15 to 20 minutes actually. So thank you so much, sir, for your presentation.
Okay. So be happy to address questions or comments. You can post them in the chat, or you can unmute yourself and speak. I've quickly gone through, I've tried to explain to you the why we need a model, what are the different kinds of models, and then I have given you a spectrum of different applications, and of course, given the time, each of the applications I just quickly sort of rushed through in terms of the context, the type of model, and then how it has been used and how it's been validated. So I thought I saw someone's hand raised. You can pose your questions in the chat, or you can raise your hand, and please don't hesitate to put a question or a comment. I will, to the best of my ability, try to answer them. Push Kumar De.
Good morning, sir.
Good morning.
I am from Wallabh Institute of Technology, West Bengal. Sir,
Yes.
actually, I asked a question to you: which data required for this modeling? Which type of data?
Which data requirement?
For modeling this model.
So each model has different kinds of data requirements, right? So some of the data requirement is from, suppose you are talking of an equipment, you have an equipment performance. you can actually run the equipment. Let's say we are talking of a pump, right? You can find out at different points how much is the head and what is the flow. And you can also find out what is the pump efficiency. So you get the pump characteristics.
Yes,
If you
sir.
are looking at a turbine, you'll have the power output against the mass flow rate. So each of the, you can have equipment characteristics, you can have environmental conditions, you can have things that you are measuring, you can put things together and then validate. So depending on the context, the data requirements would be different. But you could get this from the design value, you could get it also from the experimental value. Gnanamurthy,
Yes, sir. Good
go
morning,
ahead.
sir.
Good morning,
How
Gnanamurthy.
you are using the genetic algorithm, this type of model, how it will be, how you are comparing to the natural things?
So basically what happens is whether you use genetic algorithm or you use some other technique, it doesn't matter. In some cases, what happens is that your problem is non-linear and you don't get an exact solution. So you need to search. In this search method, what we do is we use an analogy with genetic and mutations, and essentially we create different kinds of codes which are there, and we try to compare them. You create arbitrarily, you create different types of mutations, and you find the performance of each under each mutation. When you change it, what happens? So this, by doing this, you prefer the one which is giving you the better, you go to that species which is giving you the better performance, and this is just a method for doing efficient search. So it's whether you look at genetic algorithms or you look at simulated annealing, these are all search techniques. You can also do the Newton search, and these techniques are usually done in situations where you don't get closed form analytical solutions. Okay, and
Okay.
now in many of the cases you actually have toolboxes which do most of this for you. So the technique is not that important, but in that technique, in order to validate it, you have to see, remember, in all these search methods you get a local optimum, so you have to really start with different solutions and prove that that local optimum is indeed a global optimum. When you have a physical context, of course, you know that your solution is going to lie in some range of temperatures, pressures. So that is not really too much of a problem. Often modelers are usually interested in complexity, but there is a trade-off, because the simpler you make your model, the more likely it is to be used in the real world. So
Okay.
keep your model as simple as possible, which most of the requirements of your decision context.
So one more thing, sir. How the data you are taking from the cloud or cloud data or some other journals data like that you can take it or
So, for your data sources which you are looking at, I would suggest, I know many people do their research based on other people who do their research, and as long as something is published, then you can refer to it and compare. Not a very good idea sometimes, because some of these papers are just exercises in generating papers, and the
yes.
assumptions are not necessarily correct. So you should have some connect with real life. You should try to see whether it is an industry or it is a specification, get some overall data, then you can make assumptions, because then what would happen is you would really be able to use, you'd physically understand. So as I told you in the first case, the most important thing in the model is the context. Why are you building the model? Who is going to use your model? What is it going to be used for? So in academics, what we do is we are so bothered about XYZ paper that we often forget about reality. So think about reality. There are large number of problems out there, right? So
Okay.
take a problem, understand, then you look at literature to see how people have handled. So again, there is this question in the chat. Vasant Panigrahi has
Thank,
put, I
thank you,
suggest,
sir. Thank you, lot, for
yeah,
your nice
okay.
presentation.
Yeah, some new research problem which can be done using MATLAB or some other open source software. So there are a whole host of research problems, and I think what you should do is, when you talk about the research problem, look at what is there in reality, where are the problems. If you think in terms of, for instance, today one of the problems is storage. If you're going to have higher amount of renewables, how much storage should you have? What kind of storage? How would it operate? Okay, now there is this question from Ayush Garg 172. Have we tried to capture 75% lost energy while PV conversion? One crude idea I had is to split sunlight to pure visible light. And okay, so this is a different kind of question which you are asking. I mean, this is there have been things where people are trying to look at, tandem cells where you take all elements of that spectrum and try to do that. So there are different things, but please also think of, in the case of PV, the situation may not be just about efficiency, it is also about the cost and the material, because you may have the resource, the solar resource is not constrained, and the constraint is more in terms of the area and of course the material costs. Yes, if you think, you can think in terms of different ideas to try and improve those efficiencies, and you can of course, before you look at the idea, look at the basic characteristics of your semiconductor materials and see how that would so this is where you can use a model, and you can use a model for the energy spectrum, the amount of absorbance, the kind of current characteristics that you have for different materials, and then see what would happen. The more details on that I would not be able to give, but this is something which you need to think about, try experimentally, and also you can create a sort of model. I think there was one more question. I thought someone's hand was raised. Yes, Praful, go ahead. Unmute yourself and ask your question, Praful. Okay, Rhythm, there's a question for you. Tyagarajan wanted to know whether there's a feedback link for the session.
Yes, sir. So I have one feedback for the entire course at the end of the course in the last session. So you can.
So that you have to wait to give your feedback.
Yeah.
Yeah. Okay. Is there any other questions?
Sir, any
Yes,
attendance
Biju.
link is there?
Yes, Biju.
Hello, sir.
Sir, attendance link is there?
Yes, sir. Sir, my question is concerning to the that Shunya project.
Yes.
So I would like to know a few details about those, like what is the actually average power requirement you have made upon like while deciding that what is the capacity of those PV panels. I guess the majority of the power energy requirement goes for the air conditioning. So would like to know whether it is a VCR, vapor compression system, or vapor absorption system, which will be the suitable one when we opt for the solar power systems in this.
Okay. So Biju, this was there were some specifications of the competition, and the specifications of the competition was, this competition was in France, near Paris, in Versailles. It was the house had to be a European quality house. That means it needed to be air conditioned, and we needed to also have the washing machine, cooking range, everything should be supplied. So what you are right that a significant part of the requirement was based on the air conditioning, and this was a vapor compression air conditioner with an efficient air conditioner that we had. And we used the solar thermal for the hot water in the system. We had 5 kilowatts of PV on the roof, and we reduced the loads significantly. We use mostly efficient appliances. We also have phase change material. We used insulation so that the total load got reduced, and it was a net energy positive house in that sense. If you look at the Team Shunya website, you will find there should be a detailed technical report which talks about the design of that. But this is, if you just look at it, 680 square foot house, and the peak rating was 5 kilowatt. It was an energy plus house. Yeah.
Thank you so much, sir.
Okay.
Yeah, I regularly attend that. You normally every year you arranges a course on energy management. Like I was lucky enough to attend one of those courses. Thank you so much, and I guess it is still continuing every year.
Yeah, this year I'm thinking of, I'm not yet decided what to do this year. So anyway, we'll figure out. We may do it for the oil and gas sector itself, or for one particular industry. Yeah.
Okay, so thank you so much.
Okay.
Actually, it was very nice with lot of interactive sessions and lot of tutorials, which is the crux of the course actually. Thank you. My request to the coordinator, Rhythm Singh sir, I couldn't type anything in the chat box. It is saying some like it is available only to the team members. Actually, I'm added as a guest, it seems.
But others who are guests are chatting, putting in the chat.
Yeah, I think everyone with outside IITR is a guest, but we have to participate in the chat actually.
Yeah, everyone is should be able to participate in the chat. Okay, I think we are running out of time, Rhythm.
Yes, sir.
I think there are no other questions. If anyone have it, was it or?
Heap 12 রাইস 19 রাইস মানে কি হিপ রাইস এই হিপটা তো সমান আছে রাইসটা এক ছোট হবে যদি এটিকে চেঞ্জ করব capri leggings.
If there are no further questions, shall we Rhythm?
Yes, sir. Yes, sir. Yes, sir. So we'll end this session here itself. And thank you so much, sir, once again for your valuable inputs and an amazing lecture, actually. So this was really wonderful to have you here. And thank you so much, sir.
Thanks, Rhythm. It was good. I enjoyed it. Okay, thank you all. Yeah, bye.
Thank you.
For the participants, we have a few announcements, and actually there are two major announcements. One is regarding the software tools which we'll be using in this course. So as you might have seen over the course structure, so there are three technology, especially three technologies for 3 days, which we'll be focusing on. So the second day, tomorrow, we'll be discussing about the modeling and simulation of solar energy systems, specifically. So in that case, so for solar PV modeling and simulation, we'll be using the PVSYST software. And this PVSYST, though it's a proprietary software, but it's the free, the demo version is available for 30 days as a free version. So I would request the participants that they can probably have it on their computers, and so that tomorrow, like the last session, every day will be the hands-on modeling session, where we'll try to take up some hands-on problem and do it actually in the software. So I would request the participants that they can try and install at least the demo version of PVSys today, so that when we do the hands-on modeling session tomorrow, that is available for everyone. Then the third day, that is on Wednesday, we'll be doing the biomass energy systems, and that day the software which will be used will be Aspen Plus for the modeling, for hands-on modeling part. So, but this Aspen Plus, the problem is that it's a proprietary software, and even the demo version is not available for free. So if your university or institute is already having the license, then you can use that one. But for those who will not be having, I guess many people will not be having the access. So for them, we will try to put the hands-on session in such a way that at least you can see how things are being done and what are the capabilities of the software, and accordingly, at a later date, if you want to have a licensed version of that, then you can implement those things. So that is for the biomass.
Can I add my
Yes.
one point regarding Aspen? Yeah. So hello everyone. So this Aspen Plus software should be available in the chemical engineering department of your respective universities or colleges. So just consult them if this software is available. So many universities have this. So if it is available, I would request you to procure a license. That would make the learning much more simpler for you. And we chose the software because this is the best software available. So anything that you learn on this can go a long way. So thanks, Professor. That is what I want to.
Okay. Thank you, Professor Arora, for that input. And then the fourth day, which is Thursday, as we know, that day will be dedicated to hydropower modeling and simulation. So for that thing, actually, we will be using only the mathematical and analytical modeling. So there is no need for any proprietary software. So you can just go ahead and attend, and the mathematical and analytical models will be discussed, and there'll be some practice related to that. So there's no need for proprietary software for that. So these are the few announcements regarding the software requirements. And I'm getting a few comments here regarding the details of the model software link. So I mean, PVSYST, if you just type PVSYST in, PVSYST, PVSYST in Google, then you can get it. Otherwise, also I'll share the link if needed. So that is there. And then so this was regarding the softwares. And then another announcement for today's second half after the lunch, we have a very interesting session on some light yoga and meditation and holistic development session. That's very interesting, going to be really interesting for all of you. But because there is some light, I mean, not really actual yoga, but a light version of the yoga and meditation which is there, we have planned for you to experience the thing yourself. So we would request, if possible, if you can have a light lunch, so it would be helpful. So there'll be some initial discussion, some talk around 2:30. We'll have for 40 or 45 minutes, and then 3:15 we will do some light yoga and meditation session. So I think a light lunch would be advisable for that. So these are some of the announcements from our side. I'll just enable the unmuting of participants. If someone is having any quick question regarding the course or anything related to these aspects.
What about attendance link, sir?
Yeah, the attendance you don't need to worry about. So Microsoft Teams has that inbuilt facility, and we'll just download it from our end, and we'll keep track of that.
Thank you.
Yeah.
Sir, please give the information which software we have to download.
Yeah, the software for solar PV is not PVSYST. I'll just share the link. Yeah, PVSYST. I'll just share the download link for that.
Yeah, kindly share the link in the group WhatsApp.
Sure. I'm just sharing here in the chat box itself. You can access it right away. Just a second.
Sir, chat box we cannot access actually. It is, I think you have made us guest. So WhatsApp is better.
I'll email it as well. I've just now sent it on the chat, but I'll email it also. It's so it's straight away pvsys.com/download.
Okay, sir. Thank you.
Yeah. I'll email it also, by the way, for everyone.
Okay.
Hello, sir.
Yeah, please.
Hello. The recording is available for us to view later stage.
Yeah, so how it is that recording we will be having at our end, and we'll be sharing it with AICTE, and AICTE has said that they'll be uploading it on maybe YouTube channel or some of their public media, social media. So it will be accessible to all actually, even those who have not participated in the course. It will be accessible, I think, accessible to everyone.
Okay. Thank you, sir. Thank you.
So good morning, sir. Schedule of the program.
There will be a test.
No, the test will be at the end. So the last session on Friday, 2:30, that will be the test, which will include the questions on all the sessions. So there'll be only one test at the end.
Multiple choice question?
Right. It will be multiple choice questions.
Sir, what is about the PPTs? Sharing?
Yeah, the PPTs we'll be sharing with all of you. So over the email which you have registered and on which we sent you the email links for the lectures. So on the same email, we'll be sharing the PPTs of the course.
Good morning, sir.
Yeah, good morning.
Sir, I want to ask that because my ID, I'm from the IIT Delhi, and